Okay, so the next topic that we will cover is how to optimize the gradient, the weights of our networks. So for that, we have already introduced the concept of a cost function. So that is the difference between what we want to predict and what we actually predict. That is also called the loss function. So we want to minimize the loss or minimize the cost, and we have already introduced gradient descent. So the gradient descent, the given weight is updated with the current weight minus some learning rate times the gradient of the loss function with respect to that coefficient. So the idea is that if the increasing the coefficient makes the loss larger, we want to decrease the coefficient. So that is the meaning of this minus sign. And the idea of the learning rate is that we are approximating the loss function by a line, and then how much we travel along that line. So here is the representation of that idea. So we have a loss function, we have the derivative or the gradient of the loss function with respect to a given parameter. We are showing just one parameter, so this is a local minimum and we cannot escape from there. And sometimes it is not exactly zero, but it is very flat. So it is very flat, and then we don't know exactly where to go, because we travel a bit and we get trapped into these flat regions in which the weights are no longer updated. And there are a few approaches to this gradient descent optimization. So there are kind of several variants of it. So one of them is using all the data to update our weights. So here, sorry for the change in notation, but I haven't found a similar web page to copy from. So let's say that now our cost function is Q instead of L, and then we have a set of data. So we have inputs and outputs, n pairs of those. So we put the input in, we propagate, we have an output, and then we have a difference. So that difference is Q, and for every pair we have a difference, and this difference depend on the weights of the network. So we want to update the weight of the network using the current weights minus some learning rate and the gradient of Q with respect to all weights at the same time. So this is a vector notation to do that, and that goes down to summing over all pairs the gradient of the error in that pair with respect to the weights. And we can do that using all pairs at the same time, or in the other extreme, we can do it after every pair. So we present a pair, we update the weights. We present a pair, we update the weights. So the difference between these two, this one updates after seeing, so it is the average of the updates of all pairs at the same time. So we are seeing the whole data set, and then we are going into the direction of the gradient, seeing all the values that we have in our data set. Here is after one, and you can imagine that there are situations in between. So if you have 1,000,000 points, you don't want to evaluate a million times and then taking a decision, but also going every one by one can be quite costly, because it can be quite inefficient. So you cannot compute the forward in parallel for many points, and it can also be quite noisy. So you have the concept of batch. So the batch is somewhere in between. So not using the million, not using one, but using a few. And a few sometimes it is 8, 16, 32, depends on how smooth your function is and also on how much memory you have in your GPU, because when you compute the gradient and you have to backpropagate, somehow you have to keep track of what is the error of each one of those elements in the batch, and which is the update at all layers for all the elements in the batch. So it is a compromise between the smoothness of a function, number of updates, and also GPU memory. So here we have how this stochastic gradient descent behaves. Unfortunately, this web page has already disappeared. There are alternative ones, we will see some of them. But you see that sometimes the optimization is quite noisy. So this is just this one. Sometimes you are going in the wrong direction. You want to go to this minimum, but sometimes you are going back or you are going away from the minimum. But on average, you are going closer and closer. Then we can improve this stochastic gradient descent with momentum. So the momentum is the update of the weights is not directly related to the gradient, but it goes through some velocity. So it is like an object that is moving in space, and then the object, you describe it by its position, that would be the weight, plus some velocity, and the velocity has to do with the history of that movement. So somehow this velocity, you update the velocity using the current velocity, some dampening. So now the learning rate, there are two learning rates. One for the how much you update your coordinates, so your position or your weight, and how much you update your velocity. And the velocity is the one that depends on the gradient of the loss. So this one is a dampening, so that if the loss doesn't is zero all the time, then the velocity eventually will go to zero. So there is some braking, and this one acts as an acceleration term. So this acceleration, braking, that turns into a velocity, and then the velocity is the one that updates the coordinate. So this stochastic gradient descent with momentum is an improvement of this stochastic gradient descent, and it is aimed to overcome these kind of regions. So here you're going down, you have this position, but then because you have some speed, so you have some momentum that help you to go across these regions, and also these ones here sometimes. So you have some velocity, may help you to go a little bit up, so that you can overcome small bumps. So this momentum is something great to have. And yeah, and you have two coefficients. So one to update the momentum, one to update the position, and those two, the interplay between those two, can also create their own oscillations, and so there is an interplay between the two. And one more interesting thing about how momentum is used is that it allows somehow to smooth the trajectory through this reasoning that we use here. So somehow it has some velocity to escape from there. And the other one is that it allows for a larger range of step sizes. So now the range of step sizes for which the algorithm converges is somehow modified by the convergence also of the momentum. So now you have 2 degrees of freedom to play with the optimization. Then we have Adagrad. Okay, so Adagrad. So we have the stochastic gradient descent with momentum, and this Adagrad looks like a little bit like all of them. So they are all variants of gradient descent. So here you have the gradient, and then you have the learning rate. And the learning rate, now it is not a constant, but the whole thing is now changing over time. And this is a constant just to prevent dividing by 0. And this one is what is the magnitude of the gradient. So the magnitude of the gradient, if so somehow this is updating this sum of squares of the modules of the gradient up to time t. So you compute the gradient, you compute the norm of that gradient and square it, and now you accumulate all that. So if the gradient is weak, this will be close to 0, and then close to 0 you are dividing by a smaller number, so you will make longer changes. So that makes sense. So if the function is very flat, try to travel a lot along this line. That is the meaning of that. If the function is going down very quickly, so if that is very quickly, that means that the gradient is large. And if the gradient is large, be careful, don't go down too quickly. So that is the meaning of this square root of the sum of the squares. There is a problem with this modification. That is, if you are training for too long, then there are thousands of iterations, and then you are accumulating too much, and at some point this term is very large, and then you don't allow the step to go far, even if the gradient locally is small. So this Adagrad was one step further, but then we can combine the two. So we can combine the idea of momentum with the idea of adaptive learning rates. So here this is the standard Adagrad, and now so the update of the weights is similar to the Adagrad, but now the current sum of the gradients, somehow it is smooth. If you are coming from signal processing, here you recognize an infinite impulse response filter. So that means you are making a kind of local average of what has been the magnitude squared of your loss in the last few iterations. So this alpha is a small, it's a number close to 1. So that means that basically the sum will be the same as the previous sum, plus some small update of the current loss gradient. So like that, you avoid this problem of very long trainings that somehow this saturates and don't allow the learning rate to be adapted anymore. And you can put everything in there, so you can put moment, so you update the moment, you can have velocity that is related to the magnitude of the gradients, and then you combine two. So one is the adaptive one, and then you have the moment. So you can combine the two, this RMS prop and atom, so that you can compute, you can go more and more smoothly towards the minimum. And yeah, so here in this web page we have an example of how to create different different optimizers. They are all coming, in this example, they are all coming from TensorFlow, so actually you don't have to implement all these formulas, but you need to understand what are the differences between them. So here we have an example of those. So you define a goal function that you want to minimize, and then this is the true minimum, and then you can create multiple optimizers, and then you keep track here of how x and y are calculated. And here we have an interesting part, that is this one. I think I am commenting them further in the slides. So this part here. So this part here is a tool that is given now with these libraries, TensorFlow and PyTorch, that is called the gradient tape, that somehow records the gradients for you, so that they can be used to compute the differentials. So for instance here you can see this is the most basic use of it. So let's say that you have a function y, and you define y as x squared, and then you have some value x, and then you want to compute the derivative of y with respect to x. So you can set up a gradient tape, we call it G. We tell G to watch x and see what happens with x. So the gradient tape sees that x is being used to compute y. So now you can compute what is the derivative of y at the point x, and x has been told to the gradient tape to be watched. Okay, so the derivative of y with respect to x at the point x equals 3 is 6. And yeah, so in general we can you can tell G to watch particular variables, or you may not, and then it is watching everything that is inside this scope. So it sees that you are using x and y to compute z, and then you can compute the derivative of z with respect to x, the derivative of z with respect to y, and you use the optimizer, that the optimizers have been defined here. So you use the optimizers, and the learning rates are defined at the time of creating the learning rate, the optimizer. So you optimize, you use the optimizer to apply the gradients that you have just computed here, and to update x and y. So you start with some x and y, and you want to optimize the function f. The function f, it is not here in this code, but it is here in this code. So you have defined the function f in some way, and then you use that to the different optimizers to optimize that, and then you can plot them, or making all kind of plots. So this is the minimum, should be the minimum somewhere here, and then you see how the different elements converge to this minimum. This is the global optimum, and then how they converge to there, and then you can animate that, so that probably there are some videos, so you can see how they go to there, how they oscillate, and how smoothly they go to the minimum. Okay, so this is one. The other one, the other interesting, this is the same, but now in this slide. And the other interesting idea is that the learning rate doesn't need to be constant. So we have already seen that adaptive grad, so AdaGrad, somehow adapts the learning rate depending on what is the module of the last gradient. But you can also play with that constant. So you may iterate, have some pattern, like having a large learning rate, so that will allow you to go further in your landscape, and then decrease their learning rate by factor gamma. So every 4 iterations you reduce your learning rate, or you may have this kind of behavior. So this kind of behavior is, okay, so large learning rates allow you to go far. Small learning rates allow you to explore locally and go to the local minimum without oscillations. So you start traveling much, and then reducing, and you will be here at some local minimum, and then you start again with large changes, and that will help you to have to escape from local minimum. And then you hope that by these big changes again, if you are in a local minimum, you can escape from it and find a better local minimum. If you are at the global minimum, then even if you make big changes, probably you don't go too far from the best minimum, and then you always go back to the same place. And you can combine the two, so you can combine these two ideas. So you allow some increase and then decrease and then increase and then decrease, and overall there is an overall dampening function, so that the learning rate at the end it is relatively small, and you can you don't oscillate too much around the minimum. And there is another interesting web page for that is this one. And then you see that there are many different possibilities to construct your learning rate scheduling, and very often these things are called hyperparameters. The optimizer, the learning rate schedule, the default things by the default options by most libraries, they make sense, so you don't have to touch them. But yeah, you have multiple possibilities, and what you do is you construct your scheduler, and once you have your scheduler, you have to provide it to the you can provide it to the optimizer. I don't see the code here, but you can provide the scheduler to the optimizer. So this would be it. I think we don't have anything more for this part of the session, and see you in the next one.